Applications of the vector equation to speed, time, and velocity. So here's our vector equation. And if we take our vector equation and we think about speed, time, and velocity, well, r is still the position vector of any point that's traveling along that path, which is a line. Now, instead of a being just any vector, we're going to think of this t, wow, is fancy, oh, that's nice, as time. Our t is our time. And so when time is 0, a now becomes our starting point. So where did this object start? That's at point A. Vector b, which is our direction vector, well, our direction vector becomes our velocity vector. Because if we figure out how much we're going to go in t equals 1 hour, that's going to give us our speed, and it also gives us our direction. And if we find the magnitude of our velocity vector, we find the exact speed of our object. So here we've got a vector equation of a line. We've got a starting point at 1, -1. We've got a velocity vector of 3, 4. Write down the velocity vector. So this is saying that in every unit of time, and the time here is in hours, we travel 3 to the right and 4 up. So if we draw this on our grid, our starting point is at 1, -1. That's our starting point. In 1 hour, you're going to travel 3 to the right and 4 up. You're going to go that far in 1 hour. In 2 hours, you would go double that, and so on, and this would make your vector equation of a line. But this part here would represent how far you would go in 1 hour. Well, using our magnitude formula, we can figure out the magnitude of 3, 4. That's just the square root of 3 squared plus 4 squared, which makes sense because this is 4. This is 3. That length would be 5. So if the length of our velocity vector is 5, that means you're going to travel 5 units, in this case kilometers, in 1 unit of time, in this case hours. So our speed is 5 kilometers per hour. If you had to describe this, describe the motion in words. It is traveling 5 kilometers per hour in the direction, if we write it as a vector, 3, 4. If you explain that as a direction, you could say 3 to the east, 4 to the north. Give the equation of the object's path in this form. This form has no t in it. So if we go from our equation, our vector equation, we can write our parametric equations. And from our parametric equations, we can solve for t and get our Cartesian form. So that'll be x minus 1 divided by 3 is equal to y plus 1 divided by 4. And now we would just need to rearrange this to get ax plus by equals c. So if I multiply both sides by 4, and I multiply both sides by 3, and rearrange this, I'd have 4x minus 3y equals 7. And that would be in the form that they were looking for. So now we have our parametric equations. Time is measured in seconds. Distances are measured in meters. Write down the vector equations. So our vector equation, our starting point is when time is 0. Well, that would be 4 and 5. Our direction vector, we are going 5 and -2. So in part B, which is the velocity vector? That was the direction vector. That's 5 and -2. And if you wanted to find your speed, well, what is the length of this vector? 5 squared plus 2 squared, 29. What was it, meters per second? Yes. So now this object is traveling along this path, and you plant a pole at 39, -9. Will it hit the pole? So again, if we think about our parametric equations for this one were x equals 4 plus 5t, and y equals 5 minus 2t. The question is there a time when the x-coordinate is 39? So if we go from here and say, if I make x equal to 39, and I solve for this, can you see that you get that the x-coordinate is going to be 39 when t is 7 seconds? If we're going to hit that pole, at 7 seconds, we also have to be at that y-coordinate. So now the question is, are we at -9? At t equals 7 as well? And if you solve for this, you do get 7 seconds. So yes, since those are consistent at 7 seconds, you will hit that pole. We'll do one more example. A jet is flying at a speed of 700 kilometers an hour in the direction of 2, 6, -3. Find the velocity vector. Why can't we use just 2, 6, -3 for the velocity vector? Or maybe it's right. How would we know if it is the right velocity vector? It obviously has the right direction, but the velocity vector will have the right direction and the right speed. What is the speed of this vector right now? So if we did the square root of 2 squared plus 6 squared plus -3 squared, 36, 40, 49, square root of 49 is 7. So the speed of the vector 2, 6, -3 is 7 kilometers per hour. We need a speed of 700 kilometers per hour. What should we do to our vector 2, 6, -3? Multiply it by 100. So if you multiplied it by 100, that velocity vector will have a length of 700, and so it will have a speed of 700. Now this worked out nice because to go from 7 to 700 was an easy thing to figure out, multiply by 100. But let's say, what would you do if I decided to say a jet is flying at a speed of, let's make it really slow, make it really awkward, pi kilometers per hour. So it can fly about 3.14 kilometers an hour. It's a very fast plane. So in that case, life is going to be easier if you first find the unit vector by dividing by 7 and then multiplying by pi, right? So then you would just have this one, 1 over 7, that's your unit vector. Then pi over 7 becomes a length of pi. Of course, we don't have that. That's too slow for a plane. 700 kilometers per hour instead. So we're going to leave part 2 of this with different things and more collisions possibly for another day. I will give you your exercise sheet from it already, though.